One important question to ask is, can we have a cipher that is monograph but have a huge key space? And the answer is yes. We have a simple monoalphabetic substitution cipher for this, and in this case, every letter is replaced by a letter. So idea is as follows. Write your alphabet. In these examples, I'm using the English alphabet. So you write the alphabet in the order, then write the same alphabet in a random order or in an order that of your choosing. So every letter is mapped to a letter, and sometimes you can map the same letter to itself. This is not forbidden. So your key now becomes this randomly organized letters. So this is actually a permutation. So question is, how many different keys can you have in this case? So for A, you can write 26 different letters here. Once you put one here, you have left with 25 options, 24, 23, 22, and so on. So as you can guess, in total you can have 26 factorial different keys in this cipher. And this is a very huge number, and you cannot try every key one by one in this scenario, because this number is huge even for our computational power with computers today. So you write, the idea is as follows. You have the plain text, you look at the letters, and in this plain text you replace every A with K, every B with U, every C with E, and so on. And the person who wants to decrypt the message gets your ciphertext. They know the key, so they replace every K in the ciphertext with A, every U with B, and so on. So this looks like a perfect cipher because it is resistant against brute force attacks. Attacker cannot try every key because the key space is really huge. So, and even today we cannot perform this brute force attack by computers because this number is really huge. And if you change the alphabet, for instance, for Turkish, we have 29 letters. So this cipher becomes, the key space becomes 29 factorial for the Turkish alphabet, which is even larger than this number. So for almost every language, our computers are not fast enough to try every key one by one. So this looks like a perfect cipher. So why we are not using it today? The answer is as follows. Although we cannot perform a brute force attacks, we can come up with different cryptanalysis techniques to break this cipher. And so for this reason, we should find a weakness in this cipher. And the weakness comes from the redundancy in the language. Every language has a redundancy. Some letters appear more than the others. So this is the redundancy in a language. And by using this redundancy, we can break this cipher. And this is called actual the frequency analysis. So if you capture the ciphertext, you can, by looking at it, you can somehow capture the key by performing frequency analysis. So let's talk about frequency analysis. Frequency analysis is introduced by Al-Kindi in a manuscript deciphering cryptographic messages in the 9th century. So as far as I know, this is the first known cryptanalysis book, and actually a copy is available in Topkapı Museum. So I don't know if you can visit the museum in the pandemic, but normally when you visit there, you can get a photocopy of the pages of this book. But as far as I know, it is written in Arabic. So idea is as follows. As I told you, that it is based on the redundancy of the language. So before trying to decipher a message or break the cipher, what you need to do is, for the language that you are going to attack, find a very long text and count the number of frequencies of every letter. So assume that you are going to attack or try to decipher cryptographic messages written in English using monoalphabetic substitution cipher. So you need the frequency of letters in the English language. For this, you have to find a very long English text, and most of the time what we do is to get a freely available book written in English. So you need to count the appearances of each letter. So you have to check how many times the letter A appears, B appears, and C appears. Of course, in the old times, they had to do it by hand. But today we have computers and you can write a very short and simple programming code to check or to count every letter in a text. So this actually takes less than a second for a computer to count every letter in a text. And if you divide the number of appearances by the whole total number of letters, you get the frequencies or the probabilities of the appearances of a letter. So, for example, if you do it for the English, you will observe that the letter E is the letter that appears the most. And you will also observe that the second most appearance comes from the letter T, and so on. So you can write a programming code and check what is the first and second letter in English. Of course, it depends in the language because the words change in every language. So for Turkish, if you do this experiment, you will observe that A is the letter that appears the most compared to E in English. So if the ciphertext is long enough and if you have this information for the language, now what you need to do is to count the letter that appears the most in the ciphertext. So if it is written in English, most probably that letter would be mapped to E. So you will change all of those letters to E, then find the second most frequent letter in the ciphertext and assume that it is T because of this observation we did before. And by doing this substitution, you will see that you can get the plain text. But you have to be careful because if the ciphertext is not long enough, the letter that appears the most might not be E, but maybe T. So you have to do some trial and error to get the plain text. Almost all the time it doesn't match directly, so you have to do some manual adjustments by yourself. This is also due to other reasons, because if the context is on some topic, for instance, if the plain text is about cryptography, you will see that the letter C appears more often than a regular text. So there are many reasons for this to change, but since this is a statistical attack, you have to watch for the statistics and you have to calculate the probabilities and do some manual adjustments. So this is a very good cryptanalysis technique, and most importantly, today's modern cryptanalysis techniques are also statistical attacks. So this frequency analysis gives you a basic idea behind most of the modern cryptanalysis techniques. So everybody working on cryptanalysis should know this idea. Okay, so let's move on to Digraph ciphers. So we can break monograph ciphers due to frequency analysis. A good example for Digraph ciphers is the Playfair cipher. It was invented by Charles Wheatstone in 1854. This first literal Digraph substitution cipher, it uses a 5 by 5 table containing a keyword and the rest of the alphabet. So the keyword is actually will be our key. Memorizing this key or keyword and 4 simple rules are enough to use the Playfair. But strange enough, when this was first suggested by Charles Wheatstone, British Foreign Office rejected it because of its perceived complexity. So Wheatstone offered to demonstrate that 3 out of 4 boys in a nearby school could learn to use it in 15 minutes. But the Undersecretary of the Foreign Office responded, that is very possible, but you could never teach it to attachés. So initially, British didn't use this cipher, but rest of the world start using it. And as far as I know, it was used in First World War. But Lord Playfair promoted its use, so this is why we know it by the name Playfair. So here's an example. Let's say that we want to encrypt the plaintext cybersecurity, and our key is Cryptology. Let's say we are going to use the Playfair cipher with this plaintext and with this key. So as we already said how to create this 5 by 5 table. So this is actually will be called key schedule in the future, because modern ciphers have some algorithms that help us to use the keys, which is called key schedule. So we can see this as a key schedule. So idea is as follows: create a 5 by 5 table, and first write the keyword here, but drop any duplicate letters. So for instance, Cryptology has the letter Y twice. So once you write it here, you don't write it for the second time. So every letter appears only once. So you write your keyword to the top, then you fill the table with the remaining non-used letters of the alphabet. So you get a 5 by 5 table. The problem is that the English alphabet has 26 letters. So we have to drop one. This is why we put I and J to the same place, because J is compared to other letters are rarely used. So once decrypting, the person who is decrypting the message has to decide if the letter corresponds to I or J, which is not that hard. So the following are the rules. If both letters are the same or only one letter is left, add an X after the first letter. We will see an example shortly. If the letters appear on the same row of your table, replace them with the letters to their immediate right respectively, wrapping around to the left side of the row if a letter in the original pair was on the right side of the row. So again, there is a circular notation here. If the letter appears on the same column of your table, replace them with the letters immediately below respectively, wrapping around to the top side of the column if a letter in the original pair was on the bottom side of the column. So once you go to the bottom, you start from the top again. And finally, if the letters are not on the same row or column, replace them with the letters on the same row respectively, but at the other pair of corners of the rectangle defined by the original pair. The order is important. The first letter of the encrypted pair is the one that lies on the same row as the first letter of the plaintext pair. So these are the 4 rules. They are not hard to memorize, but if you see them in an example, you will realize that they are actually very, very simple. So let's start. We write our plaintext here, but since this is a Digraph cipher, you have to pair them like this. But as you can see, cybersecurity has odd number of letters, so it ends up with Y. But our first rule says that if this happens, put an X to the end. So let's start to encrypt with CY. You find the C and Y in your table, so they are at the same row. The rule says that replace the first one with the one that is on the right, and replace the second one with the one that is on its right. So it is RP. Now we are moving to BE. Now B and E are not on the same row, or they are not on the same column, so you have to create a rectangle here. So B and E are at 2 diagonals, so L and I are on the opposite diagonal, so these will be our ciphertext letters. But as we mentioned in the rule, since the first letter is B, you have to write the letter on the opposite side of B, which is L. So it's not IL, but it is LI. So instead of BE, if you are going to encrypt EB, it will be IL. That is the main idea. Next thing is RS. Again, they are not on the same row or column, so you create a rectangle here and write the diagonals here. For EC, again, you get a rectangle. Again, you are the same. But here is a good example. No, this is not on the same column, sorry. So here is an example where I and T at the same column. So you have to replace with the I with the one that is one below it, which is S, and you replace T with the one that is one below it, which is B. And finally, Y and X are at the diagonals of a rectangle. So this is your ciphertext. So this is very easy to memorize, and it is easy to work on a 5 by 5 table. So it is easy to encrypt and decrypt. And as far as I know, it is used in First World War. So we said that frequency analysis can break any monograph substitution cipher, but since our computers are now fast enough, we can also break ciphers like Playfair, which are Digraph ciphers. So 2 letters or 3 letters, the frequencies of 2 letters or 3 letters can still be calculated by computers, and we can perform frequency analysis like attacks to substitution ciphers that use 2 or 3 letter substitutions. But if you increase the size, like if you gather 8 characters and perform a design a substitution cipher that works on 8 characters, then most probably, if you design it good, our computers will not be enough to perform frequency analysis like attacks to these ciphers. But the thing is, designing such a cipher is not easy, and you cannot still use it by using pen and paper. The good thing about Playfair was that it was very easy to use. But if you design something for 8 characters, then it will be something very hard. So if you use longer substitution, key will be too long to use or stored in practice. Encryption and decryption will become too complicated. But the good thing is that this idea of using polygraphic substitution leads to the idea of block ciphers, which will be the topic of the next week's lecture. So the main idea behind block ciphers are actually these polygraphic substitution ciphers.